Okay, so this is the video for section 4.2 for differential equations on reduction of order. This is an interesting topic. It's not a brand new method per se, but it's a way to take a second order differential equation and use a substitution to be able to reduce it to a first order differential equation so we can use the chapter 2 techniques to solve. And then we'll get into some new methods here in the next unit or next section. All right, so if you have a second order linear differential equation, if you happen to know one solution, then we can use the methods of this section to find a second solution. Okay, so this is a kind of esoteric technique, but it does have application, and we're going to need it later on in the course. Sometimes we'll know one solution and we don't have a method to directly find the second solution, but we can use this method to use reduction of order to find the second solution. Okay. All right, so the procedure is this. Given a second order differential equation and one known solution, which we're going to call y1, we're going to postulate that there is a currently unknown function u, which can be a function of the independent variable x, such that the second solution will be this u function times the first solution that we know is a solution. So if you have a given solution, you basically multiply that solution by an unknown function u and assume that the second solution is that. Then we go ahead and take the first and second derivatives of this new potential postulated solution. We plug those back into the differential equation, and that will result in a differential equation where we can do a Sybil substitution because we're going to find that the new equation, when we change all the x's get substituted out with u's, we're going to end up having that all the non-derivative u terms will cancel out. We'll see in an example how this works. And then we're going to define a new symbol w, doesn't matter what letter, but we'll just use w, to be u prime. And when we substitute, the second derivative will become a first derivative, and the first derivative will become a w. That will produce a new first order differential equation, and then we can use techniques like an integrating factor to solve for that. And that will be the solution for w, which is u prime. And then we'll take the antiderivative, we'll integrate u prime to find u. And once we have u, we can take the first solution that we were given and multiply by u to produce the second solution. Okay, I have one example for this, and then I'll show you a formula that's related to this. But the main thing in the lesson here is to go through this example. The writing on these kind of problems gets a little bit long-winded. Okay, so be aware of that. But the procedure it's of course very procedural, like all the stuff in this section. Okay, so we might have a problem like this. The indicated function is a solution of the given differential equation. Use reduction of order to find a second solution here. So here's the differential equation. Here's the solution that we know already. We have to be given one solution for this to work. Now we're going to use this solution to produce a second solution. All right, so here's how we do it. First thing we're going to do is we're going to postulate that the second solution, y2, is some function u, which is really a function of x. It could be a function of x times the first solution, okay? Okay, to keep things a little simpler, rather than have all these parentheses all the way, I'm just going to write this u as u, but we'll know that it's actually a function of x, okay? So in order to plug this solution into the differential equation, I'm going to have y prime and y double prime. So this is y. So y double prime, or y prime, I'm just going to switch to y prime. I'm not going to keep copying the 2 over and over again. Since this is a function of x, I have two factors. That means I need the product rule, right? So I'm going to take the first times the derivative of the second, which is 1/3 e to the 1/3 x, plus the second times the derivative of the first. And the derivative of the first, we don't know what the function is, so I just have to call that u prime, okay? So that's y prime. It's u times first times derivative of the second plus second times derivative of the first, and this just becomes u prime. Okay, I need a y double prime to substitute also, so I'm going to take the derivative over again. That means each of these is a product, so I'm going to have to do the product rule twice here. So it's first times the derivative of the second, which brings another 1/3 here and produces 1/9 e to the 1/3 x. That's first times derivative of the second, okay, plus second times derivative of the first, which I'm just going to write as u prime. And now I have to do the product rule for this term. So I've got first, which is e to the 1/3 times derivative of the second. So the derivative of the derivative would be the second derivative, so u double prime, okay? And then I'll have second, which is u prime, times the derivative of the first, which is 1/3 e to the, there's an x there, 1/3 x. Okay, so now I have y prime, and y double prime. So the next thing is, once we've computed this, we postulated this new function u times the first solution to produce a new solution. We take the derivatives. Then we're going to substitute that into the differential equation. So the differential equation is 6y double prime plus y prime minus y equals 0. So if this is a solution, then that has to make this equation true. So I'm going to plug this in. So it's going to be 6 times all of this. So it's going to take me multiple lines to write this, but it's all one big line. 6 over 9 u e to the 1/3 x, and then 6 times this. 6 divided by 3 is 6 divided by 3 is 2, so plus 2 e to the 1/3. There should be an x there, u prime. Okay, plus 6 times this. 6 times e to the 1/3 x u double prime. That's a 1/3. And then plus 6 over 3 is 2 e to the 1/3 x u prime. That's this part, that's this term. And then I have to add on y prime, which is this. So I'm going to add a 1/3 e to the 1/3 x u plus e to the 1/3 x u prime, and then minus y, and y is just this. So I will subtract u e to the 1/3 x. Okay. And that all has to equal 0. So let's try to combine some like terms here in terms of u. So I have a u here. Let's see, which terms involve a u? This one, and this one, and this one. So it looks like I can write that as 2/3. I have 2/3 e to the 1/3 x, and then I have plus 1/3 e to the 1/3 x minus e to the 1/3 x. And all of that is times u, okay? And then let's take all the terms that are u prime. So I have u prime there, and a u prime there, and a u prime there. So that means I'm going to have 2 e to the 1/3 x. And then from this one, I have plus 2 more e to the 1/3 x's. And this term here, I have plus e to the 1/3 x, right? And that's times u prime. And then I've also got terms that have u double prime in it. That's this one here, just this one term. So I have plus 6 e to the 1/3 x u double prime equals 0. Okay, probably some simplifying I can do in each of these. So let me go ahead and do that. If I have 2/3 plus 1/3, that's going to be 3/3, which is 1 minus 1 means this is 0. Okay, so this is going to end up being 0. So I have 0 times u. And then this one, I've got 2 plus 2 is 4 plus 1 more is 5. So I have 5 e to the 1/3 x times u prime. And then I've got this plus 6 e to the 1/3 x u double prime. Okay. So whenever you do this kind of a substitution, because of the way the product rule works out, the term with the u ends up going to 0 typically. Now, what that means is now I can do a symbol substitution. I can say, right now I've got a differential equation which has a u prime and a u double prime. Okay, so I'm going to make a symbol substitution now. I'm going to say let w, a new letter, equal u prime, which means now I can write this as 5 e to the 1/3 x w plus 6 e to the 1/3 x w prime equals 0. And this is now a first order differential equation, which means I can use the techniques from chapter 2 to solve this. Okay, so maybe I could do this. How about if I kind of put this in standard form? I'll move this term over here and say I've got w prime. Well, let's do it kind of in stages here. I'm just going to reverse the terms first. And so if I then divide everything by, let's divide everything by this leading term, 6e to the 1/3 x, 6e to the 1/3 x, 6e to the 1/3 x. We're dividing the entire equation. Then I get this. I get this cancels and gives me w prime. These cancel, and so I end up with just a constant here, 5, 6w equals 0. So here's a new first order differential equation that I can now solve. All right, so this is a linear first order differential equation. We have it in terms of y or w here. Constant coefficients. I could use a couple different methods to solve this, but let's go ahead and use the integrating factor method. So the integrating factor is going to be e to the integral of p dx, where this is p. So it's going to be e to the integral of 5/6 dx. And so that's going to end up being um, just e to the 5/6x as the integrating factor. And so then the way we proceed here is we say, all right, I know that if I just multiply the left-hand side is going to be the integrating factor times the variable w. And we start off with that being the derivative of that is equal to the right-hand side, which is 0, times the integrating factor. So if you multiply both sides by the right-hand side by the integral factor, you get something that's the derivative of the integrating factor times the dependent variable. Okay, so what we typically do then is say, okay, we have e to the 5/6x w is equal to the integral of this, which is just 0 in this case, right? And so if I take this with respect to the variable x, that means that e to the 5/6x w will equal 0 plus an integrating constant. Okay, and so then if I divide both sides by e to the 5/6x, I get that w up here now, w is equal to c times e to the negative 5/6x, right? Moving it to the top. Okay, but we define w to be u prime. So what that really means, changing colors here, is that u prime is equal to c e to the negative 5/6x, okay? Which means if I want u, I'm just going to take the antiderivative with respect to x. So if I take the antiderivative of c e to the negative 5/6x with respect to x, then u is equal to, I'm going to have to divide by this constant. So it's going to be c divided by the constant negative 5/6, right? E to the negative 5/6x, that's the antiderivative, okay? And so this whole thing is just another constant. So I'm just going to relabel this another constant. Doesn't matter what it is. It's just some constant times e to the negative 5/6x. And what that's saying is that this u function that we postulated would exist that would make this a solution can be any function of this form. So I can choose any value I want for this k. The simplest is just to let k equals 1. So I'm going to say my u function is just e to the negative 5/6x. Okay, so now what we said was that the second solution way back up here was the first solution we were given times whatever we find u to be. So that means that my second solution, y2, is just u times the first solution, and the first solution was e to the 1/3 x. And so that means since we found out that u is e to the negative 5/6x, if I multiply that times e to the 1/3 x, I will get the second solution. And so this is going to be, since it's like bases, negative 5/6x plus 1/3 x. And so this is the same as 2/6. So if I take negative 5/6 plus 2/6, I get negative 3/6, which is e to the negative 3/6 x, which just ends up being e to the negative 1/2 x. So that means that this differential equation up here has two solutions, right? One solution is e to the 1/3 x, And the other solution that we obtain from this solution is e to the negative 1/2 x. Both of these equations are solutions to the original differential equation. And that's it. This is called the method of reduction of order. And you can see why it's called that, because we start with a second order equation. By doing this substitution with the product rule, we can end up reducing the order down to a first order equation and then use our existing techniques. All right, so that's really it. Just this one example. And I think with that, that should be enough for you to attempt the homework. But there's one other thing I want to show you. Now, the book mentions this because it seems very procedural, and it really is. You can actually postulate kind of depending on the second order form. If it looks like this, where you can rearrange this to have a leading coefficient of 1, you can actually kind of go through the steps pre-solve and come up with a formula for finding this. So I'm going to show that to you, although I don't want you to resort to this formula unless you really can't make this work in some way. Okay, so if you were to take that second second order differential equation and derive by the leading coefficient, so in other words, in this one, if I were to take this and divide everything by 6 to write this as y double prime plus 1/6y prime minus 1/6y equals 0, we can call this function p and this function here q. Okay, so we can put it in this form: y double prime plus a p, which could be a function of x, y prime plus q, which could be a function of x, y. If you then do the whole procedure on this and keep these like this, you'll find that the second solution turns out to be the first solution times this. And this is the integral of a fraction where the numerator is the integrating factor with this p divided by the first solution squared. Okay, I would only resort to using this if you're having some sort of real difficulty with the computations and things, because this is difficult. You have to do an integral inside of an integral. But sometimes this is actually easier. So I'll just throw that out there. If you find that you need it, I think, let me look at the homework real quick, because I think there might be one question that where it makes sense to use it. Let's see if I can find which one it was. In section 4.2. Let's see, I did use that equation, but only on problem 11. So on problem number 11, if you want to do homework problem number 11 and use this formula, that would probably be better than trying to do it by hand. Try to do it by hand so you can kind of see why it might be necessary. And then when you get to a point where you're like, okay, this is crazy, then resort to the formula to get the solution. All right, that's it for 4.2. It's just a method to reduce the order so you can use previous methods. But the thing about this method is you have to already have one solution, and then you can use this method to find the second solution.